Cool. So hopefully all of you are here for the computational design panel. Yes? Thank you. Thank you for asking. Yes, appreciate that. Well, thank you for all being excellent at geography and reading maps and being here with us all today. My name is SJ. I'm a avid lover and passionate enthusiasm extraordinaire when it comes to things like computational design. So I'm super excited to be moderating this panel today. And I guess we'll do a round robin of introductions starting on my right. If you could give your name, your title, your company, and then I guess potentially what sparks joy for you when you think of computational design.
Hello everyone. My name's Alice Wise. I work at the MTC, or the Manufacturing Technology Centre. So I am a research engineer and I sit within the advanced design team, which basically means that I'm interested in all avenues of advanced design. That usually means computational design tools, and computational design tools tend towards additive technologies. So I do a lot of work in design for additive, but also we're interested in anything that facilitates design as a whole. So not just designing for additive or designing for manufacture, but for designing for infrastructure, designing for systems, designing for anything, basically, or as we call it, DFX. So a bit of everything, yeah. What sparks joy? I really enjoy learning new things. So I get really excited when we get the opportunity to come to events like this and hear about innovative tools, cutting edge technologies, anything that I hadn't heard about before, basically. Yeah, keeping on top of things.
God, DFX. I'm Alexander Pluk, GM and CTO of Additive Flow Division, recently Nanodimension, and a background in materials and real machine design, and just know how difficult it is to get something in the real world from idea to working assembly. And I think also what we just saw with Domin was just fantastic. Sparking joy. Well, I think joy is enabling people and engineers and manufacturers to really realize their goals as rapidly, as efficiently, as sustainably as possible.
Hi, my name is Bradley Rothenberg, founder, CEO of NTOP, formerly known as Entopology. We lightweighted our name, actually. And so, what sparked joy for me? There's actually a nice quote at the end of the last presentation along the lines of, or what sparks joy or what potential computational design has for me is really like the last quote of the presentation, like expanding the art of what's possible. So, opening up engineers to exploring new design spaces that are now, we have all of these incredible digital manufacturing technologies from 7 different types of 3D printers to advanced 5-axis machining to composite layup. I've seen all of these at our customer sites, and these machines are incredibly capable machines, but the design software itself has always been a bottleneck. And so I think computational design has the ability to kind of unbottleneck that, or open up the art of what's possible to allow us to explore, use, and tap into all the value that these machines produce.
Cool. Thanks. Hi, everybody. Thanks for arranging the Develop 3D panel. My name is Moritz. I am the Director of Engineering in Hyperganic. So essentially, my title changed from what's written here to something else now. About myself, I'm passionate about a few things. First of all, my family, my lovely girlfriend, and mountaineering, and also computational design, really. So what sparks my interest, especially in a technology-heavy company like Hyperganic, is unlocking new ways of solving complex design challenges. And I also need to reference the prior presentation where there was one quote around rethinking the way you're addressing problems, because that's essentially what we're doing with algorithmic engineering. We're starting with defining the problem, and then essentially the solution just so emerges. And every time we unlock another elegant solution to a problem, that really is what sparks my personal interest, and I guess also the interest of my team.
Hi, everybody. My name is Matt Schomper, Schomper. I spell it because the easiest way for you to get to know me is just to look me up on LinkedIn, because I talk for far too long to explain my backstory. Currently here as the CEO of Lattice Robot, I gave a new tech talk earlier this morning. I think what sparks joy for me, and most people that follow any of the stuff I do probably already know this, is I can't not see patterns in stuff, whether that's just the noise in this tablecloth right here, or whether it's a bio-inspired material from some random creature that my kids happen to be interested in at the time. So what sparks joy for me is modeling it in such a way that makes these naturally occurring metamaterials available for engineers to use in products in a broad way. I just get so much joy out of being able to see those sorts of things inside a part, and it's just cool stuff.
Awesome. Hold on to that mic, because then we're gonna run it back this way. So first question. So mainstream examples of computational design are obviously in shrimp, snazzy footwear, or rocket engines. But what other industries and products do you see as big, easy wins for comp design right now?
So Moritz and I were talking about this earlier, because I think the term low-hanging fruit is challenging, because everybody who's been in additive for any length of time knows that there's no real low-hanging fruit. It's all been quite the journey. Speaking as somebody who comes from med device, I think right now there's already been penetration into med device market and just aerospace. So the first thing I would say is, for the people that are like, additive's not a thing, well, I mean, I've designed validated parts that are living in people's bodies for the rest of their life. So absolutely, there's additive parts out there. I think maybe lower hanging fruit would be some ancillary, what I call widgets, or consumer goods that have less regulatory requirements. Once you start getting into any regulated market whatsoever, and all of your tests impose the red tape, the regulatory, like med device, aerospace, things like that, there's a significant hurdle that needs to be overcome. So I think maybe the question for me is less like if there are any or low hanging fruits, and I really just think about it more of when you look at the regulations, like what has to be overcome. And in some markets it's less than others, but I don't want to trivialize the problem.
Yeah, maybe adding on to this, it's okay. Yeah, maybe adding on to this from the discussion that we had prior. There's one success case in additive manufacturing, which is the dental aligners, really, where we have a direct-to-consumer product where people were able to go end-to-end fully and link everything together. So I think if there were that easy low-hanging fruits, then there would be more of these alike success cases. And again, coming back to the prior quote, I guess there's also a mentality shift required to really grab these low-hanging fruits.
So I mean, I think also with the aligners and that type of product, it's a product that requires a lot of customization too. And so, not every car needs to be custom to a person. And so I think you have to look at where does the digital process add value to the production. And so a lot of times we'll look at like a single bracket and be like, okay, this is an optimized bracket, it's so cool. And it actually took the engineer like weeks of work to like set up Inspire to like get an optimization to run, or set up OptiStruct and get it to run, and they get one bracket. And it's not really like you reduce the weight of the bracket like 10%. Awesome. That's great. It's a satellite that's going up in a SpaceX rocket where you're paying for a meter by meter box, not by the weight. And so what's the impact of that? But when you look at the potential of computational design, of having a system that can describe the requirements that are needed for a single bracket and get you a bracket that's going to be like 10% of the weight of an initial bracket, actually applying that to every piece of secondary structure of like a Black Hawk helicopter, for example, actually can have an impact on the overall system. And so I think where we're missing right now is like, what's the impact of the computational design of a part and how that impacts the overall systems level performance? Because that's where we're going to see that same value that aligner technology, or one of our customers like Lightforce Orthodontics, actually Aligner is also an NTOP customer too, but both of them, they're seeing the value of this ability to churn out thousands of designs a week. Actually, one of our product managers got the Lightforce braces, which is pretty cool. but to see that she has a product that actually went through our software in them. Medical device, I agree with Matt on as well, and similar application where we're seeing like mass produced, customized parts. But I think when you look at actual mechanical design, it's what is the impact of like doing a systematic computational approach to parts and how they impact the system.
I think if we look at what do we mean when we say computational design, right? Part of what we mean, or maybe feel like we should be meaning, is are we logically taking the steps of decisions in product engineering so we can have enablement and acceleration from computers to help us make the right decisions? And that's more global than design. That's why this DFX just kind of triggered in me earlier. And then if you ask the question, how does engineering touch our lives, right? It's everywhere. You know, you were talking about earlier, you know, looking at, you know, can't remember the right word, use the right word, this patterning on the table, right? You know, everything that we're interacting with has been engineered. That's passed through CAD, maybe even 2D drawings, who knows? And so this is like ever present throughout everything that we're interacting with. Brad, I agree with you in the sense it's around what's the systems of the systems. If you've optimized, you know, your hydraulics weight slightly, that means your housing is now more optimized, which means your car can drive further. Does that mean that it's more safe as well? You know, so you maybe need less bumper strength. So you have these kind of cascades of connected systems over time that will improve. And sometimes I'm looking at kind of other parallels, right? And that's why I like to talk earlier too when you're talking about, say, electronics or whatever. If you think about selling Microsoft Word right at the beginning when everyone's, you know, on typewriters and so on, where's English used? And I think it's that same global problem that can be solved by computational thinking.
It's very concise, and I'm not sure I have anything to add after those 4 answers, but I think despite the fact that this is the future fabrication stream and we're all here to talk about lattices and metamaterials and mass customization of aligners and mass customization of shoes and stuff, I think it's important not to pigeonhole ourselves into an additive route and again start to think about system scale structures. So when we have customers who are not engineering single products and they can't just think about lightweighting a bracket or increasing fluid flow through a manifold, it's about looking at things on the system level. And so there's definite need for software and PLM solutions and things like that, which tie everything together and let us have a holistic view of things. There's been a lot of AI development and machine learning development in both Siemens and SolidWorks and pretty much any of the big software manufacturers, Autodesk as well, who've got their whole research division in AI, which are all about interrogating models and letting you see, okay, I've got a particular part in my model. Do I actually want to take that out, extract it, and optimize it? Or can I, for example, use AI to search existing models and say, can I replace that with something we're already making? Can I combine these two things? We talk about when we're doing additive manufacturing, like part consolidation and stuff. So I think that's another important view, is looking at a whole system, consolidating and rethinking, can we optimize this or can we just completely eliminate it and replace it with something else? So hopefully that's still in line with the question.
Yeah, no, it's still definitely in line with the question, and it like leads into, you know, like my next sort of question, which is going to be like, what do you feel is like potentially holding back computational design? Do you think that it's like the traditional structures of thinking, like we saw a lot in like the previous presentation, or do you think it's that the physical world hasn't yet quite caught up with some of the things that we can do computationally?
I think a lot of it does come down to that conventional thinking, historical thinking of a suspension system needs to have springs in it, a bridge needs to have trusses and archways and things like that. And regardless of how many of these amazing new startup companies come out and facilitate these fantastic designs, if you take that to a large industry, a big sector, and you say redesign your entire product line using this, there's not enough buy-in. We need to have more more paperwork, more standards. As you were saying earlier, there's so many barriers to entry on things like aerospace in terms of standardizing materials, introducing anything new that's not historically been validated. That I think that is still a hurdle for us, is getting new technologies, be it additive or be it just the software approach, into old companies who are, in some cases, using legacy systems from still decades ago because that's the way they've always done it. And I think the best way that we can do that is through education and through case studies and through working with large companies, not just to have small, cool-looking components on 3D printing blogs, but actually getting them into production in commercial airplanes or commercial automotive, or getting buy-in from big customers who have more sway in the industry.
Anyone else with a suggestion on barriers besides legacy thinking?
I think it's more than just legacy thinking, right? It's where is the money? What's time to value, right? Understanding it's like multiple prongs of a change management process through all layers of a supply chain that is trillions of whatever currency you decide to use today, isn't going to happen overnight. There's going to be fast movers, medium movers, slow movers, and never movers, right? Who'll go bust because they haven't used the right technology. And I think it's when you start seeing stock market moves, I think you mentioned AI earlier. Why is it suddenly you've got this reemergence of kind of new wave AI with massive investments going in generative? Well, I think part of the reason is ChatGPT is accessible to the general public, the general population. AI has been around a long time. We've been doing it for a while. It was being done pre-compute capability, right? These neural nets being written by hand. But now, because it's accessible, you've got C-suite waking up to the fact that, oh, what's this thing? And then suddenly now, loads of investments going across all different domains of AI. I see maybe within computational engineering, computational design, computational manufacturing, there is an accessibility gap because there's so many domains, so many disciplines to make any physical product, that the accessibility question is something we need to look at. I mean, aligners came up a few times. We understand what an aligner is. We've all interacted within it. Are we going to talk about the micro-mechanical component that's been put into a heart valve, right? That you worked on, not that you did, but that you could have worked on in medical. Maybe, maybe not. So I think it's that visibility and accessibility.
Yeah, I mean, I think I agree with both of these two. I think it's the people that are the bottleneck, and it's the maybe it's the people, and then it's the business case behind what's happening, and being able to. There's like a chicken or egg problem, right? Well, I don't know if I'm going to try a new tool. Show me the business case. Well, to make the business case, I need to use the new tool, or I need to use a new way of thinking. And so I think it's up to the true innovators out there, like Matt Schomper, like yourself, SJ, like the MTC, to really show engineers what's possible and start pushing the industry forward so it's no longer just about incrementally improving the systems that we have, but it's actually producing a new breakthrough.
Also is that there's quite a big knowledge gap between the different value chain stages. So someone in a design department not necessarily does understand what's happening in manufacturing. So what you're traditionally seeing is someone designs a bracket, to stay with that example. Then this bracket gets simulated by the simulation guys, and whoever was in this process for function. So once the redesign is done, like, well, your wall thicknesses are not okay there, and it's probably not producible like this, and so it goes back. So what I want to say is there's a huge segregation between the different value chain steps, and it was somewhat already mentioned with the boundaries or hurdles along the way, and also the certifications along the way.
you, Jed.
I'm going to break the snake format and just say go on to the next question, because I don't feel like we all have to say something.
You're right. Okay. So we're about halfway through our time together. And at this point, before I go on to any of my questions, are there any questions from the audience on anything that we've covered thus far? Yes.
So, your comments about systems is very practical, right? Because, why design a new airframe when you can do it in software? When you can control the airplane with software. But we're still talking about mechanical products at this table. How would you integrate all of the software and electronics to actually make the solution, the holistic solution, better?
Me specifically.
Well, no, I mean,
I don't know. I'll give it a go. So, and I have a bit of insight because I've just come back from Israel, where Nanodimension are doing kind of these 3D printed electronic systems, right? So we're getting this and also on the convention hall, they're looking at kind of ECAD for cabling and so on. So you're starting to see this convergence between stages and scales between MCAD, ECAD, etc. I'm sure you've met, electronics engineers. You've met mechanical engineers. You're an electronics engineer. You've met mechanical engineers then, right? You've met simulation engineers. Do you use the same language when you're talking to each other? Do you have the same priorities and goals and timeframes? Sometimes, right? Hopefully. So I think it is also just a matter of time before we have overarching convergence in the future. And if you want to suggest some ideas on how we can converge most efficiently, happy to have that chat.
But also, I think the big question is, how do the requirements feed between the two disciplines? Because, how ridiculous is it that if you have an airplane that has a curved outer structure, to just put a box in that structure? That's how we put electronics in airplanes, and we have radiation-hardened boxes that fit there. And the electronics are stacked set of sheets. And so the question is then, how do you get the requirements into the electronics design so that you can build electronics with the Nanodimension tech to make curved electronics that are conformal and you can fit more electronics in that space? Or how do you get the requirements for what are needed on the electronic side into the mechanical design so that they're feeding back into one another, and then both disciplines can make decisions quicker, essentially? It's still, I would say, it's not just about the speed to get the design, but it's actually the ability to make quick decisions could get you a better design. So it's about effectiveness more so than efficiency of the design in this case, but it's more understanding the impact of how one change affects the whole system. I think it's back to the same thing earlier, which is how does a change of one little thing affect the whole system? And the quicker you could understand that, the better you can get to a good design result. And I'll also spark those exponential feedback loops where you get all the wins in a product.
So I always like to think, we're very mechanically thinking because CAD, typically you're producing structural mechanical components. But what I think is pretty fascinating about using computational design tools is from the standpoint of systems engineering. A computational design software, you can have all sorts of IOs, variables, equations. And one of the guys that I'm working with on Lattice, Blake Corder, who's a brilliant mind, and I both were joking about how we use NTOP for data processing, not for CAD design. Well, CAD design, but also data processing. So rather than using Excel spreadsheets, if I'm going to do any really complicated data manipulation with equations, and I want to be able to understand how tweaking A and B leads to some sort of variable output at the end, I don't use Excel anymore for some of these problems because the chain of equations that set up can be done in a CAD software way. Similarly, I've built entire process analysis and quoting systems inside of these computational design softwares where they don't spit out CAD at all. That's not the purpose. But using the engine, you can also start using this computational design mindset to design something other than just products. So it's interactive processes, it's engagements. I built a tolerance stack calculator in one of them, which is essentially you input a couple of parts and it essentially does all your tolerance stack equations for you, a la a software that you would have to pay a lot of money for to be able to do. And it's like, how can we utilize the tools? And it doesn't always have to just be to design a part that needs to fit in a particular domain, but it's using this computational design mindset, this parametric way of viewing things, which is give it all the inputs, let it churn through whatever its systems of equations are. So I would like to, like systems engineering is more so than just give me a physical product. It's multifaceted. It's this multi-physics assessment of whatever your design domain is to get to a solution.
I definitely feel you on that, because I've also, I'm glad that you brought out the dirty laundry, because I also use Entopology, not for Entopology, like the things that are on the website. I love using it for like processing data. And so when I was in grad school, I was feeding it different kinds of data models to see like what 3D like renderings or fields I could see, and to visualize the data that I was getting back from like participants in like a different way. Like if I looked at the problem a different way other than like on Minitab or something like that, and like these basic 2D plots, if I could see it in Entopology, would it show me something different? Would I see a pattern that I normally wouldn't be able to tell in like a 2D dimension? And then it led me down a rabbit hole that my boss got really mad about. But the people bottleneck coming back. But yeah, I totally agree with you. And like, I hear what you're saying and I feel you. Any other questions from the audience before we go on? Awesome. Thank you so much. So how do we change the conservative like legacy mindset then? Like, do you all have any tips or tricks for like getting people to think more systemically than just the part? Do you start with like, I don't know, like the business case and then work it back for your customers? Or do you have a tutorial?
Yeah, just real quick. I mean, I need to be careful about what I say here, I think. Just, I particularly am jaded sometimes towards humans in general. I'm not an optimistic when it comes to just the state of humanity and the fact that the average person in general is not particularly smart. So I think that this whole like idea about people are the bottleneck is tough, because humans are naturally suspicious of anything that they don't understand. So any new technology is immediately rejected at the outset. And then what's on top of that is, even if you can show them, here's this cool thing that I made, oh, and I've also validated all the results, they still are like, meh, you know? So there's just not like as much excitement as you get when you drink the Kool-Aid in the AM. There's still whole fields of people, especially at the large companies, these people that, you know, just because you got to move the whole organization. So I don't know that I've got a particular insight for how you do that, but I've found that you know, the very first step is to just back up whatever you say with data, because a pretty picture, like, people will be like, cool stuff, but then if you've got zero underlying data, then most of the engineers will just say, no, I'm sorry, not worth my time. So you got to at least bring a compelling subset of data to somebody to be like, okay, I'll talk. But no data, they don't want to talk to you.
Yeah, I mean, I think we've seen this with AM in processes. And so when you look at a company like our customers at Joby Aviation, they're heavy utilizers of 3D printed metal components on their production vehicle, which happens to be FAA qualified for their, not to carry passengers yet, but to do test flights and stuff like that. And, you know, the question for them is like, how were they able to fly an electric vehicle with 3D printed structural components of the airplane, when other companies, like, these are, you know, the engine case, these are the brackets that hold the flaps and the ailerons and parts like that. And then you look at other companies that spend like 20 years of research to fly a bracket that's the same exact design as the machine bracket. And so, I mean, I think the question is like, how do you work within the existing processes but push the limits? So like Lightforce Orthodontics, for example, for the FAA qualification of their braces, they normally, when you FAA qualify a process, they would show a Teamcenter or a PLM workflow that has the change management and change control. And they were like, we don't really want to pay for Teamcenter and build out a whole Teamcenter integration. Can we dig into the FDA requirements and like, can we show the same change tracking on top of GitHub, which is a free tool? And they were able to pass the FDA qualification process with the GitHub as their PLM system rather than a traditional PLM system, through working through. It was very clever.
Yeah.
Now, that was a software engineer who was driving the process, who maybe had some different levels of thinking. But I think it's that willingness to really get down to first principles of like, what are you actually trying to solve for? And what's the best way of solving that? And let's build that and test it and fly. I mean, Joby spent a lot of effort into testing to make sure this plane would still work with the AM components. But they did it, and they invested that research, and now I wish that stuff would be like more publicized, so other companies why can a Joby do that, but like a Boeing can't or an Airbus can't, right?
It's a secret, which is actually a joke, bad joke, but it's actually one of the reasons why there is maybe a legacy fall with lack of exposure. Because companies that are leading in these areas, so computational design, physics, getting very advanced technologies, are keeping it secret. And that makes sense. That's their IP. That's how they're going to unlock. And I think, where is that middle ground that allows these leaders to share the outcomes of their secret processes without giving the game away that's going to lose their competitive advantage? And I think you're right to say, framing it just as a people problem, that there's these, old conservative people, that they're holding back all of the smart young guys or girls who are doing whatever they're doing. That's not necessarily the case. And I've been in a room with some very senior people who have said, I did my PhD on this 20 years ago, and you're changing these material properties, and you're changing this. So I get what you mean, but I'm just not going to tell anyone that we're doing it. So I think there's the behind the fold and there's above the fold.
I think mirroring that, and also your point, Matt, on the inherent suspicion that people have around anything new. I think it's like any new technology coming into any new industry. Like if you look at petrol cars versus electric cars or something, why have electric cars now recently come to the forefold? Because everyone else is doing it, and if you're not making an electric vehicle, you're going to get left in the dust. Now that we're seeing all these big players in software manufacturing, Autodesk, Dassault Systems, SolidWorks, everyone is looking into AI, every single one of them.
What are you doing?
All of the independents and the smaller startups, as well as the large industries, absolutely everyone has their own AI division. They are all offering generative designer solutions. All of them have an algorithmic modeling platform. All of them are looking at doing closed loop, physics-driven design or whatever, because they know that that is where the future is going and that you cannot afford not to be doing that anymore. And I think that, so it's still a problem getting around okay, how do we get companies actually using these new tools that the software manufacturers are offering? But I think all the big vendors know that that is the way it's going. And if you don't get in now, companies are realizing that they're never going to get in. And I think that jealousy and keeping up with the Joneses is probably the biggest motivation for anyone to actually get in.
FOMO, I like that one.
Yeah, FOMO, exactly.
For me personally, it's seeing is believing. I had a cranky old British boss. Sorry, no harp.
Yeah.
And the first time I ever brought NTOP out, I had the free license, and I had whipped it out, and I was like, yeah, check out this cool gyroid thing that I've designed on the software. And he was like, your fancy software does not make a printable part. And I was like, oh, okay, well then, yeah, sure. And he's like, you can't slice it. And I was like, well, then sit down. And so the moment he turned his back, I got it sliced. I loaded it on the printer. I snuck it onto a build. I got it printed. And the moment I dropped it on his desk and he saw it in the physical world, from the computer into the real world. And I was like, what are your objections now? It really started changing the attitudes around the office. Then he was taking it to meetings yeah, have you seen this? Have you seen this new thing that we're doing over, in the lab? You should come by sometime. You should check it out. This is this great new computational design, flashy, shiny thing. And I don't know. That's just my own personal.
I think the solution is you.
No,
I think so.
Yeah, essentially, it's finding the right partners to get started with, I would say. So if you want to impress the big boys, you need to start with a bunch of small boys proving something, and then I guess it works. And girls, yes, you're right, and between.
But I was also going to say, with your story, it's really interesting because if people are the bottleneck, they're also the biggest accelerator to making stuff happen. At the end of the day, we are making, not myself, but the industry itself is pushing everything forward. And I think that, on one hand, the mindset of people could be a bottleneck, but on the other hand, they could be the biggest accelerator. And so maybe I kind of agree with what you're saying. It's like, see it, you gotta make it.
Yeah.
I was just going to say that the whole FOMO thing and people coming out with tools can be a double-edged sword, because I think it pushes the market ahead as a whole, but I think there's also lots of different lingo nowadays. I mean, this whole idea about Lattice Robot is trying to coalesce disparate knowledge into one place. Like, what's a lattice? I don't know. Why would you use lattice A versus B versus any of the other 400 that are out there? I don't know. Like, let's try to figure out this. So I think in the same way, softwares that are all using disparate language. I mean, and again, not to knock on any one stance in it, but there's sort of, field-driven optimization, generative design, algorithmic design. And I think sometimes all this stuff coming to the forefront, everybody's got their own tool, their own flavor of something, can also be confusing for users of traditional CAD, which has solidified over the last, several decades. So everyone knows what an extrude is. Everyone understands surface modeling. Everyone knows what a loft is and revolve features. But when you start talking about these new terms, I think it also makes people, again, suspicious. It's like, all right, well, I got my traditional CAD suite. I talk with customers all the time about this. They're like, why do I need a generative design software on top of the licenses I already have? This seems unnecessary for throwing a lattice in a part. So I think we also have to be very descriptive about what the services are actually offering, and why we feel like it's important for their particular point in the CAD journey. Because I do think that, again, at least the suspicion of, are you actually offering me something that it changes the game, and why is it any different than any of the other 4 or 5 or 10 computational design softwares that are out there?
Maybe one important point is the accessibility with this. So if you're offering a lot of different tools, and I think everybody's brand marking something, I mean, who of you knows that it's FFF and not FDM as a printing technique, right? In the end of the day, it's a brand marked new name. And so obviously all these companies, and us included, try to brand mark something because that's our name is attached to this. I guess fair enough. But if you make these tools accessible, and so the value proposition also can essentially penetrate into the core organization, and not only the young guns use them, but essentially all the traditional CAD users are able to use their workflow, and on top of that, use these tools effectively to generate value. I think then it's a win-win for everybody.
You're right.
All right. Are you ready for your last question? So a lot of these models require heavy computational power that will realistically need to be cloud-based. Are you seeing cloud-first infrastructures being demanded by companies now? Are there means by which these models can get to be less data-heavy? You were twitchy palms there. So
GPU accelerate. Yeah, GPU accelerate. Hush. So I think, it doesn't necessarily need to compute, right? So you've got, we're all kind of doing GPU stuff, I'm guessing, right? We all are. It's very fast. You don't need to go to massive cloud. You can go to cloud. You can do local. We've got AI models now that are thousands of times faster to compute. We did something in 2 weeks that took 8 seconds versus 54 hours, right? We're all using AI models too. So we don't necessarily need to go to cloud, and cloud's great. It has, other advantages like Colab, et cetera, et cetera. But things can be accessible. They don't have to cost millions of dollars of some mysterious center somewhere where my data's being lost.
I don't think your data is lost. It's usually stored.
Scary. It's so scary. Austin, can you change my process down to put my data in the cloud?
Well, it depends on what you're doing on cloud, I guess. If you're doing simulations, not everybody has a super cluster in their office to do heavy CFD computations. So it kind of makes sense to have cloud. We personally, we as Hypergenic chose to go for cloud because of some obvious reasons. One of them being accessibility, another one being AI, a topic that has been discussed quite a lot, and the third one being obviously the compute power. Because if you really want to reach everybody, you need to provide the services so everybody can use your tool fully. There's no means in providing a tool to someone, and then in the end of the day, they're just stuck in front of the tool, and you're like, what did you deliver to me? What did I buy into myself? So we try, as a software vendor, you try to essentially take this risk away from the end user. So I can see the cloud makes sense.
I think it's also like the cloud combined with new data representation. So like mesh-free, matrix-free, structural, thermal, CFD analysis, using an implicitly defined model, not a BREP-based surface model, not having to go through meshing, because you could avoid a lot of the compute problems if you don't have to do the heavy computation or store a lot of data in some ways. But I think naturally these lighter weight formats make sense for cloud or for clusters, where it's like you can have a cluster of GPUs that run a mesh-free lattice Boltzmann simulation, or you can run, there's interesting research out of Carnegie Mellon for Monte Carlo physics from Keenan Crane's group, which is mesh-free, matrix-free, built for GPU analysis. It's very researchy right now, but I think that's like the next generation of things to come, where it's, how do you reduce the data overhead so things can become much lighter weight?
Yeah, just one more comment on cloud computing since we're on it. I have worked with many companies over the last few years in specifically defense security sector, where it doesn't matter how secure a company will claim their cloud to be, the fact that the servers are not local, even if they're in Europe and if they're in America, then that's just a complete no-go for certain companies because of data protection laws and things like that. So there are a handful of industries and a few large companies for which cloud computing is not at the moment and potentially never will be an option exclusively because of their IP and their data security laws that they have in place internally. So in those scenarios, it will be things like having an on-site local installation, having a supercomputer, using GPU acceleration and things like that, because there just isn't an alternative.
I definitely feel that because I spent the last 2 years in new space, and the new space guys are great, but they don't want Daddy Bezos to have any access to their data. And Amazon Web Services, we call it AWS. And so I was just like, oh yeah, you just load it to the AWS, and oh, we can't use the AWS. And I was like, why? And they're like, oh, because Bezos owns it. And I'm like, why would Bezos own AWS? And then people are like, it stands for Amazon Web Services. And I was like, I see. What were you going to add?
It's just a short joke. Essentially, it's always with new technology, they're the ones that come first, and then they're the ones that come after that. So I guess also with cloud computing, over time, I guess it's gonna facilitate itself.
Also close to that, right?
But also,
go ahead. Sorry.
well, I here.
No, Brad, go on.
No.
We're too polite. Look how polite we are.
I'm in England.
Oh yeah, you're right. As the Romans. Go ahead.
No.
So I think these internal. I'm not going to say sorry. It's okay. I was in Canada for a year, but so yeah, these closed cloud. So I think it is about compute. Compute capability is really important because the more compute you have, the more you can do, and it's much cheaper. To one of my friends recently said, you can burn compute time is cheaper than burning material, and so that's the kind of mindset that's nice.
Unless you're F1 and you have a limited number of runs of CFD analysis, that's where that becomes a problem. But I don't know why it really matters so much whether it's cloud or local. What matters is having multiple GPUs somewhere that you can use to solve hard problems, or multiple cores of processors. And in order to do that, the technology stack that we build upon has to support solving hard problems on multiple GPUs, like StarCCM with using the AMGX solver now, which is great, and they can run these massive problems. And so I think it's most important to just understand, yes, we need a ton of compute, whether that's cloud or whether that's local. There's going to be different deployments. And I don't think we have the same level of headaches that we had 10 years ago with doing local deployments versus cloud deployments, with now being able to containerize stuff and different things like that. So things are getting better in that regard.
All right, we've got 5 minutes left. Any other questions from the audience?
So I feel like computational design, and particularly generative, is very much about automating the solution finding. And I wonder whether you could speak to, as a panel, how to identify and set the parameters that guide the computational design. Because it's very difficult to know what the specifications of the outcome are going to be before start getting into the development process. So yeah, what kind of analysis do you take to setting the parameters for the computation?
I think Alice should answer this question. You're MTC, you're the specialists in this.
Yeah, that's a difficult question because generative design, topology optimization, anything that's looking at honing in on a particular solution requires you to have some goal in mind. So let's ignore generative for a moment and just look at topology optimization. Even though topology optimization theoretically gives you one result, it's not giving you a full swathe like a generative process would, you're still required to give it something like a volume fraction, exactly. You need to have a mass target in mind, you need to have a volume fraction in mind, and then usually you'll also have a load of different varying weight functions that you feed in, which at the moment are quite human driven. And so if I decide something needs to have a 0.3 cutoff versus a 0.6 cutoff when I get my output of my mesh and I decide that's my solidification number, I'll get two completely different results from theoretically a process that was supposed to give me one. And that's just an optimization problem. So then you look at in generative design, now we don't have one factor that we're converging of, we have 10 different optimization goals. Is a benefit and also an added difficulty because a lot of the tools now, specifically in generative, you will give it a gamut of optimization parameters with a minimum and a maximum. And then it will generate you the 10,000 million whatever results that you have. And then from that, you can plot them all on a graph between factor A and factor B. At some point, you need to have someone in your company say, these two factors are what's important to me so that you can actually close in on a result. And at the end of the day, all of that is driven by requirements capture, which is not a computational design problem, that is a design problem. And again, there's not really any getting over requirements capture. It's very, very necessary in every industry. Back to loop round and AI, because that's what I've been working on lately. There are a lot of new tools which are using NLP to assess requirements and turn those into some actual tangible metrics, as opposed to spurious, it should do this, it could do that. And so I think the next development, in my opinion, is going to be around that. It's going to be around using machine learning to quantify and codify requirements into tangible numerical things.
And side note, I put Alice on the spot just now because we worked together for a whole year and that was her first project since we joined MTC, and we were doing multi-material stuff with Airbus and RF and so on. And she answered this problem for us, and she solved these requirements capture.
Just look at me now.
Exactly, look at that. So I think it does come down to people, and I think just as an overarching point, when we're looking at things like AI and computational engineering and so on, I think there can be a fear from those who haven't necessarily used the tools, this is going to somehow replace my job. Am I going to, be made redundant based on this new technology? And I think we should actually look at it totally the other way. There's hundreds and thousands and limitless opportunities and problems to solve on this planet in companies, and there's not enough engineers. We're short of engineers, we're short of design thinking, we're short of simulation experts, material experts. And these tools have the ability to empower people who've spent 3 months, I can't remember when, a great degree, right? But like a few months in a role to suddenly solve a really difficult problem that Airbus was struggling with. So I think that's what these tools can do to empower people.
Yeah.
So I'd say on requirements, the reason why FDA codified and one of the things in the law was getting rid of ambiguous and conflicting requirements, because people were struggling so much to just define the problem in the first place, and they would define a suite of 60 inputs, and 10 of them would be conflicting and some of them would be ambiguous, so there was no clear way to validate or verify them. So that's a great answer. You just have to scope it out. I think the other thing I would say about requirements and bracketing a problem is computational design, in my opinion, allows us to view requirements shifting through time a little bit differently, or how we define our requirements. One of the fun things I did recently was define an algorithm that produced a load case, ran a simulation, made a structure where the structure was essentially not needed. It trimmed pieces off of it, and then it reran, but because the connection points, some of them were no longer there, the next simulation was entirely different that time. So then it ran another loop. So if you just looked at it over 10 loops, the structure evolved in a way that an engineering mind may not necessarily converge on. In a way that topology optimization converges to a single solution, this evolutionary algorithm produced a series of potential choices, all of which totally changed over time. Think about something like a tree. You know, a tree is not static. As it grows, it changes its load requirements based upon the things that are input. As engineers, we design static systems that we want to last for 10, 20, 30, 100, 1,000 years as a monument. That's less sustainable in today's world than looking at product design as something that needs to live inside of the world for the rest of its natural life. Or 10 years down the road, we may want to disassemble this thing and reconstitute it into something different. We don't think that way as engineers. I think there's a little bit of pride and almost a God complex of, I'm designing this thing, it's going to live in somebody's body for the rest of their life, look at how great I am, rather than thinking, no, this thing gets absorbed into somebody's body, so the true masterful design craft is designing something that eventually the body absorbs. It doesn't exist anymore. And I think that confliction and being able to use simulated approaches to be able to analyze the change of material properties over time as something resorbs that's biological in nature is fascinating to me, and changes the methodology from, again, these monoliths that we design that are perpetual for thousands of years. Look at my name on this, to something that that just doesn't matter. It doesn't exist anymore. So it's like I was never even designing it.
Are we out of time? Yes, we are at time. So big round of applause for my panelists, please.
And also a big round of applause to SJ. Like, fantastic facilitation. Thank you.